Ever wondered what would happen if the impossible became real? Let's find out. Imagine stepping outside on a quiet night and looking up at the sky. Instead of the familiar gray crater-covered moon that we all know, you see a massive glowing orb shimmering with pure electric charge. No mountains, no dust, no rock, just an enormous sphere made entirely of electrons. It sounds impossible, and in fact it is, but let's pretend for a moment that such a thing could exist. What would actually happen if our moon were made only of electrons? The short answer is that it would be catastrophic for the moon, catastrophic for the Earth, and catastrophic for the entire solar system. But to really understand why, we need to take this thought experiment step by step. First, let's think about how massive the moon actually is. The real moon has a mass of about 73 quintillion metric tons, or in scientific notation, 7.35 times 10 to the power of 22 kilograms. Its radius is just over 1,700 kilometers, and it is made mostly of rock, iron, and dust. Now imagine swapping out every single atom and replacing it with nothing but electrons. The problem is that electrons are unbelievably tiny and light. A single electron weighs just 9.1 times 10 to the negative 31 kilograms. To get a moon with the same mass as the one we see in the night sky, you would need roughly 8 times 10 to the 52 electrons. That's an unimaginably huge number. For context, the entire observable universe contains about 10 to the 80 protons and neutrons. Our electron moon would contain a number of particles that begins to approach universal scales, and yet all of them would be the same charge. And here lies the first and biggest problem. Electrons absolutely hate being near each other. They all carry a negative charge and like charges repel. In the normal moon, atoms stick together because positive protons attract negative electrons, and gravity keeps the whole body together. But in this electron moon there are no protons, no atoms, no balance. Just trillions upon trillions of negative charges packed together. It would be like trying to force a billion magnets to touch north to north. The repulsion would be overwhelming. We can describe this repulsion using Coulomb's law, which tells us that the force between two charges is equal to a constant multiplied by the product of their charges divided by the square of the distance between them. For two electrons separated by 1 meter, the force is incredibly tiny, about 10 to the negative 28 newtons. But scale that up to a sphere containing 10 to the 52 electrons, each pushing against all the others, and the repulsive force becomes mind-bending. In fact, it completely overpowers gravity. Gravity is the weakest of the 4 fundamental forces in the universe. Between two protons, the electrical repulsion is about 10 to the 36 times stronger than their gravitational attraction. That means even the tiniest pair of charges completely dwarfs the pull of gravity. On Earth, gravity seems strong because it acts on huge masses, but when you compare it directly to electric force, it's not even close. So in an electron moon, gravity stands no chance of keeping those charges together. The instant you replace the moon with electrons, the sphere would begin to tear itself apart. So how fast would this destruction happen? Almost instantly. Each electron would feel the push of all the others, and because they are so light, they would accelerate outward at nearly the speed of light. The moon wouldn't crumble slowly, it would explode in a burst of pure charge. The energy released in that explosion is beyond anything we normally encounter. We can estimate it using the electrostatic potential energy of a charged sphere, which depends on the total charge squared divided by the radius. Plugging in numbers for a moon-sized sphere gives an energy release that dwarfs even the brightest supernovae. The moon wouldn't just vanish, it would become the single most violent explosion the solar system had ever seen. And the Earth would not be spared. Our planet orbits only 384,000 kilometers away from the moon. When the electron moon detonates, a storm of negative charges races toward us. Earth, which is electrically neutral overall, suddenly finds itself bombarded by an unimaginable wave of electrons. The atmosphere would light up with electrical discharges. The sky would become a constant global lightning storm as the planet struggled to absorb or repel the flood of charge. Oceans would fizz violently as electrons collided with protons and water molecules, splitting them into hydrogen gas. The very air could ignite in places, and the planet's magnetic field would twist and buckle under the stress. In short, an electron moon would not just destroy itself. It would almost certainly destroy the Earth with it. So clearly, a moon made entirely of electrons is not something the universe allows. But that's the beauty of a thought experiment like this. It pushes us to explore the limits of physics, to see what happens when we break the delicate balance of forces that hold matter together. And before we end this segment, there's one more question to consider. If such a bizarre object couldn't survive under normal conditions, is there any way, any at all, that an electron moon could be stable even for a short time? So the question is, could there be any way at all to stabilize a moon made only of electrons? At first glance the answer seems like an obvious no, but physics sometimes has strange loopholes. In laboratories on Earth, scientists have actually managed to trap clouds of electrons using magnetic and electric fields. Devices called penning traps can confine them for long periods of time, holding them in place despite their constant repulsion. But those are tiny systems, holding perhaps millions or billions of electrons at once. Scaling this idea up to something the size of the moon would be beyond absurd. The magnetic field required would be so extreme that it would make even the strongest pulsars in the universe look weak. A pulsar can have a magnetic field trillions of times stronger than Earth's, and yet to hold together a moon of electrons, you would need something greater still. There is simply no natural way for such a field to exist, let alone for it to remain stable for billions of years. But let's not stop there. If electrons are compressed close together, they don't behave like ordinary matter anymore. Quantum mechanics begins to dominate, and the strange rules of degeneracy pressure come into play. In stars that have burned out, the leftover core of carbon and oxygen is supported against collapse by the pressure of electrons. This is called a white dwarf. The electrons resist being pushed into the same state because of the Pauli exclusion principle, a quantum law that says no two electrons can occupy the same quantum state at the same time. This degeneracy pressure can be incredibly powerful, strong enough to hold up an entire star. But notice the difference. In a white dwarf there are still atomic nuclei present, positive charges to balance the negative ones. In our moon made only of electrons there is nothing to balance. Degeneracy pressure might briefly push back against collapse, but the overwhelming repulsion of like charges would not lead to stability. Instead of a quiet, dense star, the sphere would still rip itself apart, leaving behind a violent cloud of radiation and particles. Now, some people might wonder what would happen if our electron moon were to meet its antimatter counterpart, a moon made entirely of positrons. Positrons are the mirror image of electrons with the same mass but opposite positive charge. If the two spheres came into contact, the result would be total annihilation. Every electron would meet a positron, and together they would vanish, releasing their mass as pure energy in the form of gamma rays. The amount of energy released would be beyond comprehension. It would be like detonating billions of nuclear arsenals all at once. The flash of radiation would likely sterilize the inner solar system instantly. In fact, even from light years away such an explosion would outshine entire galaxies for a brief moment. Fortunately, there is no natural way for such oppositely charged moons to form, but it gives us a sense of just how much raw energy is hidden in the matter that makes up our universe. But let's step back and think about the Earth itself. Even if the electron moon didn't instantly explode, its presence in orbit would still change everything. For one, the gravitational pull that creates tides on Earth would vanish. No more rising and falling seas, no more rhythmic cycles that shape coastal life. Without tides, ocean circulation would be disrupted, nutrients would not mix as efficiently, and ecosystems that rely on these patterns would collapse. Coral reefs, tidal flats, and countless species would vanish. On longer timescales, the Earth's tilt and rotation, which are stabilized by the moon's gravitational presence, would begin to wobble. Our seasons would become erratic, climates would shift unpredictably, and the planet's habitability would be threatened even without the explosion. The moon is not just a pretty face in the night sky. It is one of the reasons Earth is as stable as it is. The irony here is that even in its impossible form, the electron moon reminds us just how delicate our universe really is. Matter as we know it exists because of balance. Every electron is paired with a proton somewhere. Every atom has its charges cancel out so that the whole structure is stable. Break that balance and everything falls apart. A moon of electrons is not just unstable, it is fundamentally impossible because the laws of physics themselves demand symmetry. Without that symmetry you cannot build stars, you cannot build planets, and you certainly cannot build life. But let's take this even further. If such an electron moon somehow appeared and exploded, what would happen to the solar system as a whole? The wave of electrons blasting outward would carry so much energy that it could strip atmospheres from other planets. Mars, already fragile, would lose what little it has left. Venus, with its dense clouds, might flare like a torch as charged particles ripped apart its molecules. Even the outer planets could be disturbed as magnetic fields across the solar system twisted under the stress. The Sun itself would likely remain unbothered. It is far too massive and too hot for a wave of electrons to make much difference. But the orderly arrangement of planets would be disrupted for good. The solar system would be scarred forever by the brief existence of an impossible moon. And yet, there is something profoundly beautiful about this thought experiment. It shows us the unimaginable scales of energy hidden in everyday matter. It reminds us that gravity, the force we think of as dominant, is in fact the weakest of them all. It demonstrates that without balance between forces, between positive and negative, between attraction and repulsion, the universe simply cannot exist. So the next time you look up at the moon, be thankful that it is made of ordinary rock. Be thankful that it orbits peacefully, tugging at our oceans and stabilizing our planet. And maybe just for a moment, imagine what the night sky would look like if it weren't a calm, cratered sphere but instead a raging storm of pure electricity. Imagine the burst of light, the storm of fire, the annihilation of worlds. It is terrifying, but it is also awe-inspiring. Because the truth is, the moon of electrons will never exist. But the fact that we can even imagine it, the fact that we can use physics to follow the chain of events from an impossible starting point all the way to the end of the solar system, is a reminder of just how powerful human curiosity really is. And that is the real lesson here. Not that an electron moon would destroy us, but that the rules of the universe are consistent enough that we can predict what would happen, even in the strangest of scenarios. Our ability to think through the impossible is one of the things that makes us human. It is what allows us to dream, to explore, and to understand our place in the cosmos. So, what if the moon were made entirely of electrons? The answer is simple. It couldn't exist, it wouldn't last, and if it somehow appeared, it would unleash chaos beyond imagination. But by asking the question, we glimpse the immense power hidden in the building blocks of reality, and we learn once again to appreciate the delicate, beautiful balance that makes life possible. Stay curious and keep asking, how if,